Hello and welcome to this new video into which we will continue the linear fitting with the least square method. Last time we worked on Meyer's method that consisted in dividing the point cloud in half, and now we are working on statistical parameters. So this is a completely different way to find a fitting line. We have to know first how to find out the value of some statistical parameters that are useful in bivariate statistics. They will be useful for linear fitting with the least square method and also for statistical prediction with the rate method. Let's discover in this first video these parameters. We are interested in finding the means of each variable. So with simplified formulas, we can say that the mean of x will be the sum of the x values divided by the number of values, and same for y. So the number n being the number of pairs xy from the study. We are interested in variances and standard deviations. So let's show the Koenig's formulas for variances. Koenig's formulas that tell us to calculate the average value of the x squared and to subtract the square of the average value of the x, which is not the same. Okay, another way to write this formula could be v of x equals e of x squared minus e of x itself squared. So we will see that in details with some detailed calculations in a further video. Same formula for y, and by definition, the square root of variances are standard deviations, denoted with the letter S or here sigma, the Greek letter, which is our S. Variance in the end is positive in any case, so we always can extract a square root of this variance and define the standard deviation. The standard deviation itself is defined as the average distance between the x values and their mean. Then we need an additional parameter because until these formulas, we just calculated some parameters for x and some parameters for y separately, but we're interested in the correlation between x and y, so the common evolution, okay, of y compared to the evolution of x. So we need a parameter that expresses both values of x and y into one calculation. We just have to mix the formulas of the variances by putting not x squared or y squared, but x times x times y, sorry. So it will be named the covariance, and the formula is this one, looking like the formulas of variances, but mixing them. The result of the covariance will be commented, so we will comment on that with examples, but it will be a very interesting parameter for us in statistics, and this will lead to the calculation of additional parameters like the linear correlation coefficient or the slope of the linear fitting line, and so on. So here are our needs. Our calculator doesn't give us exactly that. So let's see now what our calculator is able to give us. If you enter the data series, so the values of x, the values of y, and maybe if you've got a crossed table, the values of frequencies, and if you tell your calculator that these informations are in list 1, list 2, and maybe list 3, and so on, here are the results given by the calculator. So you can recognize inside that the means, okay, x bar, y bar, so no problem, you don't have to calculate a mean. You can see the standard deviations, so you don't have to calculate the variances and then to calculate the square root of them, and so on, you've got the standard deviations. But your calculator won't give you the variances and the covariance. Yet, these parameters will be important for us for some calculations. So, we have to be able to use our formulas and to finish the calculations by ourselves of variances and covariance. So, thanks for us. The calculator calculated the sums that we need in these formulas. The sum of x squared is calculated by the calculator. Same for y, and the sum of x times y. Okay, sum xy. So as you can see, you've got 5 different sums here, and you never need to calculate any sum by yourself. Okay, you don't have to square the values and then to add them to obtain a result. This result will be given. So let's see all of that in examples and calculate what doesn't be calculated by the calculator. So in details, we've got in the first part of exercise 9 a list series that represents an amount of fertilizer that has been spread, and besides on the right, the quantity that has been harvested, so the harvested production after that. So let's name in blue the variable x and in pink the variable y. Well, you've got to enter this data series into your calculator, and it's good news, your calculator works with lists. So you just have to enter this data series in list 1 for the blue column and in list 2 for the pink column. For example, list 1, list 2, of course, and tell your calculator you entered it at this location. So in Ocasio, in your settings, okay, calc set, you have to tell your calculator in bivariate statistics, the x are in list 1, the y's are in list 2, and there are no frequencies list. Then with Texas, you have to use the key stat, of course, edit to enter data in lists, and then calc to choose stat to var, and to notice that, or to make your calculator notice that you need list 1 and list 2. In the most models of calculator now, you've got just a page to fill with X list, list 1, Y list, list 2, and frec list, nothing. Okay, so when there is no frequency list, you have to tell 1 to Ocasio and nothing to Texas. That's a little difference between them. Why 1 in Ocasio? Because if there were a third column mentioning the number of individuals for each pair xy, well, if you've got a series list or a list series, you can see that one pair xy correspond to one individual. Okay, so you've got here numbers that are numbers of plots in agriculture where the quantity of fertilizer has been spread. So an additional column would be represented by values 1, 1, 1, 1, 1, 1, one individual each time. So that's why 1. And for Texas, the information is there is no third column. Okay, if you do that correctly, you will obtain this kind of results displayed by the calculator. Maybe not E of x, but x bar. Okay, I just wanted to show you another way to denote the average value of something, of some variable. And the numbers are these ones. So you can say that the average amount of fertilizer here is 134 kilograms per hectare, with a standard deviation of 48.8 kilograms per hectare. For the harvested production, you've got 44.6 as an average and 4.58 or 59 for a standard deviation, and so on. And then you have by yourself to finish the calculations of the variances and the covariance. A variance. So let's display it directly. Corresponds to this formula, Koenig's theorem. The sum of x squared has been calculated by the calculator, 101,700, divided by 5. So this is a value that is given, in fact, by the calculator. 5, this is the number of pairs xy, 5 rows here in this chart. And as a result here, 2,384, which is positive, obviously, and whose square root equals 48.826. So, well, same for y again, using, of course, the result calculated on y, exactly in parallel of x, okay? And for the covariance, you have to use a mixed formula, so the sum of x, y, which has been calculated by the calculator, 30,900 here, and surely not sum of x times sum of y, it doesn't work, okay? You just have to take exactly the same parameter that you need in the formula and it's given by the calculator, the same writing. So this value divided by 5 minus the product of the average values, 203.6. So which can be interpreted from the covariance in itself is not its value, but is its sign. A covariance can be positive or negative. It depends on the data series. So this is why there are no co-standard deviation. Okay, you can't anytime calculate the square root of a covariance if it's negative, of course. So what does the sign of the covariance mean? It's a bit like a derivative of a function. If you've got a function, and let's take the example of an increasing function, you will have a positive derivative. If you've got here a positive covariance, that means that the point cloud shows some trend to the growth of y when x increases. Okay, so when x is bigger, most of time y will be bigger. And you can have a closer look in the table. A low value of x gives a low value of y, and a big value of x gives a big value of y. Okay, and it appears like that in general in the table. So it don't have to appear each time in each row of the chart, but if it appears in the majority of the rows, okay, then you will have a positive covariance. So that's not the derivative of a function with a nice curve in your frame, but that's the trend of a point cloud, the global trend. And of course, in case of a negative covariance, it means that y tends to decrease as x tends to increase. Well, let's see a second example. It will be important because a data series in Bivariate statistics is not always given by a list series, but could be given by a contingency table. This time, the values of x and y are crossed, and in each crossing you can find several individuals. It's often viewed when you are building classes, okay? So intervals of values. In this study, we asked people about their age, so X in blue, and about the number of times they went to the cinema for the last 12 months. And again, we've got classes, okay? So intervals or some categories of answers. So known, 1 to 11, to 12 to 23, and at least 24. So there are several people into each crossing, okay? For example, there are 16 people that are between 25 and 50-year-old in this survey, and that answered a number between 1 and 11. So this time, you can't enter this way the data series into your calculator. Your calculator always works with lists. So you have to unfold this chart and to make it a list series. That means that you've got to use three lists here because you've got three information, three different kind of information, values of x, values of y, and frequencies. Let's begin with frequencies by using, for example, the list 3, and let's put them in the same list. Okay, it's very important in your calculator. You have to put the 12 values in the same list. Just take note of the order that you choose. Okay, so I choose here to put the first column, then the second, then the third. Okay, one above the other. So in list 1 and list 2, we must have the correct values of x and y that correspond to each value in list 3. So let's just see the simple organization of this table, and let's take the middle of each class. So it will be very important. For example, the three first values here, the three first frequencies, all correspond to the same value of x, which is 20, okay, the middle of the class. So that's why we have to write in list 1 4 times the number 20. And then for the four following values, we've got the value 37.5, the average value of 25 and 50. And then, oh, well, there is a little problem here. How much could we choose if we're talking about 50 and more year-old people? Well, the statement of the exercise 9 tells us to take 60. Okay, so you can't create it by yourself. The exercise must tell you. That's why in list 1 you will find this list. Now, the values of y corresponding to each value in list 3, they are organized a different way, of course, because if you can read 4, 10, 13, 6, it corresponds to the four different values of y, which will be repeated again and again. So what are these values of y? So 0 to begin, and then the average between 1 and 11, so 6, the average between 12 and 23, so 17.5, and then an average value for the 24 and more. The exercise tells us to take 36. So you've got here an organization that is different from the first table, but that contains exactly the same information. Okay, so into a list series here, so that your calculator will be able to calculate all the wanted results. Just tell your calculator in the settings that there is a third list for frequencies in this case. This time you will obtain, if that goes well, these results, and you will be able, the same way as earlier, to calculate variances and the covariance. The variances are these values. So of course you could take the standard deviation and square it, okay, to obtain the variance. So just be accurate in the decimals, okay, take a large number of decimals. The variance of y and the covariance, which is this time negative, which implies that mostly the older the people are, the less they went to the cinemas from the 12 last months. And that's what the distribution of frequencies, or you can say quotes here, shows us. Yes, indeed, for the 15-25-year-old people, they went to the cinema mostly between 1 and 23 times, mostly. But for the 50-year-old and more, mostly they didn't go to the cinema or 1 to 11 times. Okay, so let's say that the most important frequencies in each column slide to the top if you slide to the right. Okay, so if x tends to increase, y tends to decrease for the maximum number of people, sorry, for the majority of people. So this is the global trend. Of course, there are exceptions, okay? There are young people that never went to the cinema, and there are older people that went a lot to the cinema, but there are little frequencies compared to the most important ones. Okay, let's now have a break and see you to a new video in which we will talk about least square method, a simple way. Bye and see you.